the complex roots of unity or the complex roots of 1. In our previous example, we found that the roots of 8i were equally spaced around a circle of modulus 2. I want to use the fact that the roots are equally spaced around the circle to quickly find the roots of 1 without having to express in mod arg form. First, I need to find just one root, 1/5 root of 1. An obvious root is 1 itself. So I can start with one root is 1, as 1 to the 5 is 1. I'll plot that root on the Argand diagram down here. Z to the 1 is equal to 1. Now there are other roots of 1 as well that are complex numbers, and these roots will be equally spaced around this circle of radius 1. So what I need to do now is I need to divide the circle up into 5 equal sections. So I'll do that here, and here, and here, and here. Each of these sections has divided 2 pi into 5, so this angle in here will be 2 pi over 5. This angle in here will similarly be 2 pi on 5, and so on for all of the other sections as well. This then allows me to actually express the other roots in mod arg form very quickly. The circle is radius 1, so the modulus is always 1. This root up here, this will be a root of 1, and it will be Z2, which is cos I sine of 2 pi on 5 as its argument. This root here, we'll call this one Z3. It'll be cos I sine of 4 pi on 5. Roots, remember, keeping in mind that the argument must be expressed between 0 and pi, or 0 and negative pi. For these roots down the bottom, we'll come back from 0 around this way. We'll call this root Z4, and it will be cos I sine of negative 2 pi on 5. This root over here we'll call Z5, and that's cos I sine of negative 4 pi on 5. And there we have 5 roots of unity expressed in mod arg form, all equally spaced around the diagram. Just a quick note, for when you do these sorts of questions in the HSC, the examiners will expect to see the roots in quite an accurate position and on a nice circle so that they are all the same distance from the centre. Over here, what I'd like to do is a second example. In this case, I want to explore z to the 6 is equal to negative 1. Sounds a little bit unusual in terms of real numbers that we could raise to an even power and get a negative answer. So for our initial root, we shouldn't look for a real number, we should look for an imaginary number. We'll start with the most obvious imaginary number, I, and we'll check it out. I to the 6, that's I squared all cubed, which is negative 1 cubed, which is negative 1. So hence z is equal to I is our first solution. So z equals I, we'll place that here as I, and we'll call that z1. Now again, these roots are going to be equally spaced around the Argand diagram. Being z to the 6, we're looking for 6 roots. So again, we'll divide from I, we'll divide the circle up into 6 equal spacings. One will come down here. Remember, we're starting from I, so from I, this will be 2 pi on 6, which we know is actually pi on 3. This angle in here will similarly be pi on 3. And so on around the circle, or pi on 3. So again, it's not very hard to write these in mod arg form. I've got that one as I, I've called that Z1, so I'll call this one over here Z2. This will be cos I sine. Now the argument is the turning from the x-axis around here, and that turning will be half of pi on 3, which is pi on 6. Go past this one, come over here, so this is pi on 2 around to here, and I have another pi on 3. Pi on 2 plus pi on 3 is 5 pi on 6. So this one I'll call Z3, and that's cos I sine of 5 pi on 6. I now have 3 roots down here. Again, I need negative arguments, so this will be cos I sine of negative pi on 6. This one will be negative I, and the final one over here will be negative pi on 2 minus pi on 3, cos I sine of negative 5 pi on 6. A quick and easy way to find the complex roots of unity, or complex roots of 1.